Hello? Can you hear me? Someone?
Yeah, I hear you.
Yeah.
Hear me?
Yeah.
Yeah.
Can everyone do the same? I hope so. Yeah, if Ryan can hear me, others should also be able to.
Yeah.
Yeah.
I can hear you loud and clear.
Okay, 1, 2, 3, 4, 5, 6, 7, 8 of us here. So I think we are all of us here. I'm the last one. Yeah. Okay. Thank you for doing this at a very odd time. So 9 o'clock in the night. So, but I thought we should get going, I suppose. Otherwise, every lecture we were getting postponed. So we did get Niranjan's contract going. So that means that surely I won't have to do that on Thursday again. If you're not aware, I was canceling classes because I had to make up, or what is it? I had to substitute for Niranjan because he's a new faculty in our department and his contract had not gone through. So okay.
Okay.
So yeah. I should go over the syllabus, I suppose. And yeah, so I can only see your names typed, so only Ryan is on the video, so that's okay. There is a syllabus. I cannot give you the syllabus, of course, physically. That's what we would have done in a classroom. So you need to go to the, how do you do this? Let me give you a link.
Go to that same
course
web page link.
Right. But let me do that. If one of you can reach there, then you can put that on the chat. But meanwhile, let me try to type it. Specs.
I have put the link.
Oh, perfect. Okay. Yeah. So if you guys could reach there, I have to reach there.
Yep. Found it.
Okay. Could all of you guys reach there? Could you tell me? Everyone is very quiet.
Yep. I'm there.
I'm already there.
Me too.
You do okay. Dilakshi, Pradeep,
Yeah, I'm there.
and Pooja. Like you two are the new students. That's why I'm specifically picking your names.
Yes, Professor, I'm here.
Okay, cool. Nahida and Praveen, I assume you must have reached there. Yeah. Okay. So let me reach there. Okay. And you guys cannot see my mouse. Okay, so there is on the somewhere in general information on the 4th line under general information, there is syllabus for the course. Click on that, so you should see the syllabus. Okay.
Yep.
So I'll go over this in the next maybe 15-20 minutes, probably not even that, and then we can do something related to the homework that is due in a week. Okay, so most of you have taken my course before. I think you're 7 of you, 5 of you have taken my course before, so systematics and the logistics will remain pretty much the same. Pradeep and Pooja, you're new, so you should pay more attention, but feel free to stop me, right? So broadly, so this is I think you all know my name. I don't have to tell this. I'm Shajesh. You can read this, I guess, hopefully.
Yeah, I can read it.
So
Yeah.
I'm Shajesh, and this is physics 510 classical mechanics. So make sure you're in the right place. But I think in this delayed place, we all know that we even know each other already. So, okay. So how do we go about this? So let me. So in the syllabus, you will see a few things written. First thing is, of course, this is classical mechanics. And broadly, what we will do is, even though when we do Newtonian mechanics, we talk about a lot of forces, but here we will restrict ourselves to forces that are conservative. So you can say that classical mechanics is nothing but a study of conservative forces. So that's very simplistically, that's what we are going to be talking about. What are conservative forces? Anyone?
So aren't they the fundamental forces? Like the electrostatic, gravity, the
Good.
weak and nuclear forces?
That's correct. Those are all, most or all of the fundamental forces are conservative, but at a more definition level, how would you check if a force is conservative or not, or anything else you want to add on to that?
It's all connected. If you can connect all the forces in one loop, or the entire force in a system is conserved, it's the
Yeah, I
same
think
force.
what we are
that's
trying to say is that the work done by a conservative force is given by dr. So you go
Yeah.
along the path and you integrate from an initial point to final point. That's defined to be the work done by a force. But then if you go
Yeah.
around and make a circular loop,
Yep.
right, then it should be exactly zero, right? The work done for a conservative force, you go around in a loop and you come back, that's exactly equal to zero. So that's the definition of a conservative force. Or we can also say that the curl of the force, like curl, remember the gradient operator and the curl operator that you study, if this comes out to be equal to zero, that's another way of saying it's conservative force. It's one implies the other, different ways of saying it. Or that's one property, that's second, this should be equal to zero, right? So this should be equal to zero. And another possibility is that if the force can be written as a gradient of a potential energy, that's also implies that it is a conservative force. In fact, it is one and only, if and only condition. Like if you cannot write a potential energy associated with a force, then it's not conservative. If you cannot have the curl to be equal to zero, then it's not a conservative force. So, and we will discuss, we'll broadly see that this is what it is all about. In that case, we can write a Lagrangian for the system, we can write a Hamiltonian for the system, and we can, instead of discussing Newton's laws, we can talk in terms of the Hamiltonian and Lagrangian. That's what classical mechanics is broadly about. That's if you want an overview of what it is. But when it comes to logistics, we will have quiz in this course. There will be homework. There will be exams, midterm exams. There will be 2 midterm exams. So let's say midterm exam, midterm. Right, there will be 2 of them, and there will be a final exam. This will be 10% of the course. This will be 30% of the course. This is 20 plus 20. So there will be 2 exams. So that's 20 plus 20, and the final exam will be 20%. So overall, that should make up 100% for this. There is only one thing I would advise, which those of you who have taken this course before, I have done this before and it has worked out well, and that is that the quiz is unusual in the sense that homework, you have a typed out homework problems for you. There is already a homework available on the web page. So homework number 1 is due on next Thursday, which is next Tuesday, January 30th, which is Tuesday. Okay. And it is due at 4:30 p.m. Since it is due at 4:30 p.m., that means it need not be in the classroom. You are welcome to submit it in the classroom, but if not, make it due in the mail room. Everyone knows where the mail room is, Pradeep and Pooja?
Yes, I know.
Yeah,
The
so
opposite of Shannon office.
correct. Opposite of Shan's office, we have mail rooms for every faculty and teaching assistants. Because you interact with students, you have mail rooms, so you just submit it in my mailbox. The mail room closes at 4:30. That's why the timing is 4:30. You miss by 4:30, then it gets late. So make sure it is not very late. So that's homework 1. And I should stress on the quiz part. Quiz does not have a written format to it. It is mostly in the fly. We are going in a classroom and something comes up as a discussion. And if I like it, I just say that this becomes a quiz. And I'll mention that it is a quiz. Often the question is not very well phrased. It may not even be a correct question. The answer may not exist. All that is perfectly okay. It is your duty to phrase a question. That's the first part. Even the question is phrased by you guys. So all of you guys might come up with a different question in a sense, but I mostly try to define it well. And there is a recording for this. So most often you can go and see the recording and then you write an answer for that. You don't have to spend too much time on the answers. It's your choice. But if you like it, you can spend as much time as you want. This is a participation dependent course. Even if you get it wrong, you get all the points that you need. There is no late submissions allowed. So let's not do that. And earlier I used to agree the fact that even if you say that, okay, I forgot, I used to give those. Let's become a little more serious. You have to submit something to get it graded. Just saying that I forgot is not a possibility. Is that clear, Pradeep and Pooja? Like others probably know the
It's
mechanism.
clear.
Is that clear, Pradeep?
Yeah.
Yeah, Pooja?
Yeah.
Okay, so, and this also, later on, I do a curve for the course. That means to say that after a midterm exam, I feel that the exam is very hard. So I try to give some points back to you. And that depends on this. If you don't participate in this, you might think it is only 10%, but then you also lose on the curve factor. So make sure you add on to that. So my recommendation is that in this first lecture, if you don't get anything, just accept the fact that quiz is important. Don't neglect it. Both quiz and the homework is important. Those are the places where it is easy to score. Exams are harder to score. That you might not be able to help much, but these are the places where you can score. It's okay to talk to your friends. It's okay to look at your friends' homework. Everything is allowed. You can use resources. You can use solutions. You can come and ask me that I don't understand this question, and I will try to help you out. All that is perfectly fine. Try to get the homework done somehow or the other and do the learning that way. So that's broadly what the course is. are going to be about, and we can start doing something that will be relevant for the homework. Anything else I should mention? Those of you who have taken, can you think of something that I should be mentioning?
Yeah, I have one question.
Yes, Pradeep.
For the quiz,
Mhm.
we will get the time like for example, we take the one quiz today, and then we get the time for today, or just for 20 minutes, or what's the
It will be due on the next lecture, whenever we meet next.
okay?
Okay, is that clear? So
So that
today's
would be
quiz,
like a long type problem, or it's a technical question?
for example, let us say today's quiz. What can today's quiz be? Today's quiz can be. So this is today's quiz. Okay. What is a conservative force? Okay. So now that's it. That's my question. Now you can go and write an essay on it. You can refer to a video on it. You can look up whatever that is, and that's perfectly fine. And I suggest that you don't write a 10-page essay on it. That will take a long time. Write half a page, limit it to half a page, let us say. And remember, correct and wrong is not a problem. It's a participation-based question. So what is needed is that you have to make sure you attend to the lecture and make sure whenever I say quiz, you should get your radar on, and you should, oh, that is a quiz. So I should note it down. And then you submit it next time. You phrase the question. I don't even have to tell you this question. If the question is not clear, you phrase the question around something related to whatever I said. Did that help?
Oh yeah.
Right.
Yeah.
So that
This is
could be
actual quiz question, or it's just for the example now?
no. This is an actual quiz question.
Okay.
The quizzes are kind of meant to be fun.
Yeah, so
just
this is
kind of
quiz
expand
one.
further.
And
Okay.
it's not necessary that there will be one quiz problem. Sometimes there are 5 quiz problems in a quiz, in a lecture. Sometimes it is 0.
Okay.
Okay, so you have to pay attention and talk to each other. What has happened in the past is that I know you guys make a group, make a chat group, and find out what is a quiz. That's all perfectly fine with me. As far as you collaborate and get it done, that's okay.
Okay,
However you do that.
Thank
Or
you.
maybe these days you have, what is it called? AI generated. You can actually get the, like a recorded lecture, you can get a transcript of the whole lecture. And then you search for the word quiz in it. Be creative. I don't know. I mean, or just attend the lecture. Easiest is to attend the lecture and just pay attention to where the quiz is instead of doing all that way around it. Okay. So quiz 2, just to give you a feel for how a quiz can be very non-trivial. What's the radius of the universe? Right? So it's not even related to probably what we are going to be doing. So what is it? I mean, just answer something. Okay. Does that give you a feel for what quiz is going to be like?
Yeah, we get the feel, perfect feel.
Okay. Who's there? Is it clear?
Yeah, it's clear.
Okay, cool. And anything else you think I should be stressing on? Those who have taken the course before? Anything that I say will help?
Yeah. Just attend lecture and watch out for the quizzes. Be on the lookout for them.
And it's due the next lecture, before the next hour, in the first few minutes of the next lecture. Let's put it.
Okay, next means Thursday?
Thursday, yeah. As far as I know, we will meet at 9:35 in Neckers 410. This is only on the first day we are having an online online lecture. We will be physically meeting in 410 at 9:35.
Okay.
There shouldn't be any problem. There is one more question. In the previous semesters, on the request of students, the lectures has been recorded and made available to you all on the web page itself. I usually make a YouTube playlist and provide it to you guys. And do you want it?
Yeah, we need.
Is there anyone who doesn't like the idea of recording and making it available? Write an email to me.
Oh,
if
that's
you have
fine.
Any reservation?
Don't like that. You make the lecture video, yeah?
Yeah. Again, if there is a request from all of you guys, then let's have that lecture. Write to me separately if you think you don't like the idea, and then we will address that somewhere else. Okay, so generally that is no problem. In the past, I have not had any issues, so that should be okay. It also means that when lectures are recorded, it is made available on YouTube. Even though I don't make it available at a public level, that means if you search for it, you won't find it. But still, if someone has a link, you're available as a recorded object. It is there. So be at least present yourself carefully in that sense. Don't say things that you don't want to be 20 years down the line. It shouldn't affect you, right? So be aware of that. That's the only recommendation I'll give. Recording has its own. You're all familiar with it, I guess. Okay.
Yeah, be
Oh.
thoughtful of what you're saying.
Reasonable. Okay. That's it, I suppose. Do you think I should be talking about the curve? The equation for the curve? I think we can talk about that another time on the first day exam.
Yeah.
Ryan, you say I should, Manuka, do you think I should?
Do it another time.
Okay.
Yeah,
So this is late in the night, so at least we should have something going. Otherwise, just making it simple might not be worth the time effort you're putting in. Okay, so Newton's laws. Let's review Newton's laws. Remember, there is a homework due next week, Tuesday. So this all should be useful. So what is Newton's law? Anyone? Let's say second law.
force equals ma. Force equals mass times acceleration. It's the second law.
Correct, perfectly fine.
And
So we say we are interested in an object. So that's a system if you want. Right. We say that we first choose what we are interested in, whose motion are we interested in. That's this mass. It could be as big as a galaxy. It could be as small as a proton or an electron, and that's perfectly fine. And we are interested in the motion of that object. That's acceleration. That's A. And that's motion. Notice motion often we say is associated with velocity, but that's not necessarily true. You can always go to the rest frame of that object and velocity can be removed in a sense. So motion, strictly speaking, let's say quote unquote, right, is associated with acceleration. So if you're interested in the motion of the mass m, then Newton tells us that you have to only vectorially add all the forces acting on the mass m. So you have to identify, recognize what are the forces acting on the mass m, and then vectorially add them, right? So sum of the forces is equal to mass times acceleration. Force helps the motion. If you want motion to be more, then you will increase the force. Mass comes in the denominator, so mass resists motion. Force helps motion. Mass resists motion because it's in the denominator, and so sometimes you also say it's the inertia associated with motion. Let's look at what are the forces you're familiar with. Tell me any force that you've come across. Anything?
Coulomb's force.
Tell it again.
Coulomb force.
Coulomb force.
Coulomb force. Yeah, good. So Coulomb Yeah, second,
I think friction also work there.
friction, sliding and kinetic friction, I suppose. Like that's a friction you mean, I guess.
Yeah.
Tension.
Tension, yeah, force of tension. Anything else?
Compression.
What's that?
Compression.
Help me again. I think I'm not able to.
Compression.
Compression. So when you
The-
compress something, probably, yeah, why not compression? Let's say I'll write just
The
as-
opposite of tension.
Yeah, it's probably related to
Tension.
tension. Anything else?
Nuclear force.
Nuclear force. Okay,
The
good.
strong and weak.
Yes, strong and weak. Let me write it as strong and weak. Any other forces?
Gravity.
Gravity, good. That
We
was
can do the
some time
magnet.
for the list jump. That was one of the first forces we have said. Gravity, yeah, good. What else?
We can go the magnetic force of attraction. So
Yeah, sure, great. Yeah, so magnetic forces. More?
The centripetal force.
Centripetal is,
Well, I guess it's a pseudo force.
or it's accelerate. I mean, that's almost the sum of these forces is equal, contributes to centripetal acceleration. Centripetal force is not really a force, right? So it
Yeah.
could be any force that contributes to the centripetal acceleration. Right, so that's a very generic term. It's not a specific force, I guess. Anything else you can think of? Maybe normal force. That's something
No,
that we use,
no.
right? Or mostly, I think you got most of them. Maybe spring force, right?
yeah, electrostatic force.
Electrostatic is Coulomb,
Okay.
like normal and spring, right?
Yeah, spring force. Or
The
Hooke's
Coulomb
law.
is electrostatic, I guess.
Okay.
Anything else you can think of? I cannot. Oh, drag maybe.
Oh yeah, drag. Well, I guess that's air resistance, which is friction.
Yeah, but this is sliding and kinetic friction, I guess. Yeah, but drag maybe. Yeah. Right.
I think we can go with the muscular kind of force. We can use that.
Muscular, yeah, why not? Yeah, something maybe that can be classified into tension. Yeah, but I would say it depends on how you classify it. Yeah, maybe muscular forces, surely.
I think that comes with the tension, I guess.
Yeah, maybe. Okay. But you see the point that these are sort of a list. It's not a complete list. Now, what I want you to tell me is, give me expression for each of these forces. Okay. Let's start with Coulomb. That's clear, right? It is 1/4 pi epsilon naught. Right. So then there is Q1, Q2 over R squared. Right. That's Coulomb force. And then there is an R hat direction, right? It's you connect the line joining 1 and 2, and that's good. What about friction?
R.
Oh, friction would be this, like a static coefficient of the material,
Yeah, and
and
The reactive was R.
the normal force, I suppose, right?
Yeah.
Yep. Normal.
But the normal force is not really known, right?
It's just the opposite of the gravitational
Gravitational.
force.
Let's begin with normal force. What is the normal force? What's the expression for a normal force?
Plus mg or opposite
Not
of
necessarily,
gravity.
right? If you're on an incline, it is not an
Oh, then it'll be sine of theta.
Yeah.
configuration.
Or
So
cosine,
it
yeah.
seems like we don't have an expression for the normal force, right? Would that be right to say? We usually
Yeah.
relate it to another force. For a given configuration, you say that, oh, if it is a flat surface, you are standing, oh, it's equal to mg. But normal force itself, it seems like we don't have an expression. Right? Is that right to say?
Okay.
Right? We don't
Yeah.
seem to have an expression for normal force.
No,
So, in a sense, we don't have an expression here. What about friction? Going back to the list.
that means you don't have much of a expression for frictional force.
Friction either, because friction is given in terms of the normal force.
Normal force.
So if you don't know the normal force, you don't have friction too much. So there's no expression there either. What about tension? We don't have a full expression
Nope.
for
Yeah.
tension either. Compression
Same thing
either.
with compression.
Strong force, we don't study it. You haven't studied it yet. It turns out that you have, but it's not in terms of a force, it is as an energy. This is their gravity, yes, we do know that it is G M1, M2,
Or scale.
right? And magnetic force is QV cross B, right? We can even make it better expression, so that is a concrete force for that. Spring force is minus KX. Yes, we have.
Yep.
So this has drag force. Yes, so it is. Let's say it is a linear drag, so it is B times velocity, right? So apparently we have this. We don't have strong force. Yes, weak force, but we didn't. Probably you never encountered strong and weak. That's at an abstract level. That's there. That's not there. Correct. So many of the forces that you studied, it was a cheat. You never gave an expression. You just said that it exists, and then you equate it to something else. So if not for Newton's laws, you won't know anything. In a sense, it was a cheat, but it really helps because bridges are built on that. Most of what we do as a technological level, we do manage to do a lot of things there. So we shouldn't underestimate that either. But what I want to bring out the fact is that we are interested in forces like this, where you have a expression. Notice the Coulomb and gravity. What does it depend on? That depends on distance, position, right? It has a R dependence in it. So let's talk about position dependent forces. So position dependent forces. Right, instead of classifying it as forces itself, so there is one is position dependent forces. That means force that has R in it. It could be a vector R or it could be a scalar R. So here we say the force is position dependent, R dependent. Okay, so that's position dependent forces. And second one, which shows up, so position dependent forces again is Coulomb, gravity, and the spring, right? Those are the three position dependent forces in this. There are velocity dependent forces also. Velocity dependent forces. In that case, F force is velocity dependent. And of course, why not? We can have both position and velocity in them. And there is also one more feature that, remember that R is a function of time, right? Implicitly, the position depends on time. It's usually an implicit dependence, and velocity dependence on time. In general, a force could be dependent on time, position, and velocity. Right?
Yep.
And whenever we have such an expression, we will notice that at least we can attempt on talking about conservative forces. If you have an expression, at least we can do this curl and other things. We can do the integral and check whether it's conservative or not. In other places we don't even know what to do, because most of the time we don't know what the forces are, right? So at least one minimal requirement, or at least one nice feature, is that when you have an expression, then you can work with it. And where do you find that expression? There is spring, drag, mostly Coulomb, and gravity and magnetism. So we will work mostly with gravity. That will be our favorite in this course. We will talk about planetary motion, but also magnetism and electrostatics will be discussed a lot. So that's where it shows up. So let's start with position dependent. In your homework, there are two problems. One is a position dependent force. No, actually, both are velocity dependent forces. One is a drag force, and the second is magnetism. A magnetic force, QV cross B. That's a velocity dependent force. So those are the two problems you discuss in your homework. Here, let me discuss a simple position dependent force. Make it simple. Let's say on Earth, we have a radially, there is a meteor that is falling all the way from a certain height, and it is radially falling down, so that we don't have to worry about angle. Well, let's do an example associated with it. Any comments or questions you have on this? Anyone?
No.
Nope.
Okay. Okay, so let's do an example. Okay. Example. Let's make a simple scenario. Let's say uniform gravity. Uniform gravity means that Earth is flat. That means we are talking about a sphere of infinite radius, and everywhere it is flat. So then it is like the in electrostatics. If you have a conducting plate, then you have uniform electric field. Similarly, if you have a flat surface, quiz number 3, right? How should I phrase the question? Derive the fact that gravitational field is a constant for a flat surface. Flat surface means it's of infinite radius, right? It keeps going. So you have a mass that is distributed on a plane, and calculate and show me that the gravitational field associated with that will be constant. Okay.
Okay.
Okay, so we have 3 quiz problems.
Take the question. Can you repeat the question? We have to copy the question.
Yeah. Think of electricity. If you have a plane conductor, right? So that means you have a charge, positive charge, let's say Q. And if I have positive charge plate, correct? So then the F force on this charge would be Q times an electric field where this is constant, right? Uniform. It comes out to be constant, right? Do the same thing for mass. Now you have a massive plate. Probably you want to hear we say charge per unit area, right? Sigma is charge per unit area. Electric field is dependent on charge per unit area. Here, you want to talk about mass per unit area. And calculate G for this. So at this point, or everywhere around, calculate G. Is that clear? Like the electric field for a plate, uniformly charged plate, comes out to be sigma over epsilon naught. It could be epsilon naught or 2 epsilon naught, depending on whether it's a conductor or not, and times z hat. Similarly, there should be something here multiplied by z hat for a infinite plate. Okay, calculate that. Okay, is that clear, the question?
I think so.
Yep.
Okay. Okay, so we say that there is uniform gravity, let's say. I'm not deriving that. And so let's say that's a surface of Earth, ground, right? Surface of Earth. And let's say this is reasonably, this is really flat, right? And G is down. And V is up, right? So that's V. Okay, that's here. And let's say you throw a stone up in the air, right? So this goes up and then it comes down. So there's a lot of mechanics you can do. And you would say that your equations are mass times. So while it is on up in the let's say air, there is no air resistance, so neglect air resistance. So you would say m, this is the mass m, times the acceleration a is equal to, there's only one force, it is uniform gravity, so it is minus mg. It's a vector equation, but everything is happening along a straight line. So I can forget the vector and say it is ma is equal to minus mg. Right? Probably. And then you want to say that, oh, acceleration cancels out, correct? So this is nothing but, so sorry, not acceleration cancels out, mass cancels out. So it is dv by dt is equal to minus g. Right. What can I do? Let me multiply both sides with velocity v. Like I'm just doing some manipulation so that I can get some known result. And when I multiply this velocity, notice that d by dt of half v squared is equal to v times dv by dt. That's something like kinetic energy. Notice if you have put in a mass there, there is a kinetic energy in there. So this is nothing but time derivative of half v squared. And this is nothing but velocity is dx by dt. So that's minus d by dt of g times x. It's in the z direction. So let me say it is g times z. Correct? Put this on the left hand side, and I learned that this is the time derivative of multiply by mass, just so that we can identify some quantity of mv squared plus mgz is equal to 0. Right? I pull this to the left hand side, and I learned that this is equal to to mg z. Clear? So I have, this is kinetic energy. That's the potential energy associated with a ball in uniform gravity. Only in uniform gravity you can write that as mg times z. If derivative of something is 0, then you say that must be constant. Right? So it's half mv squared plus mgz is equal to a constant, which you can say is the total energy of the object, right? Just something very familiar. That's one of the simplest problems, right? You have something falling under gravity, and you can write that as kinetic energy plus potential energy is equal to 0. And let's say that, let's make it very specific. Let's say it starts from an initial point where the height, or z, is exactly equal to some constant r, and later I want to think of this as a radius of Earth, right? So this is not really Earth, right? We are saying this is of infinite, even though we are imagining this to be Earth. So it should be very close to the surface of Earth if you want uniform gravity. So you really are talking about a situation where it is of infinite radius and you're dropping something from the radius r. It's some constant r, that's all. Yeah. And let's say its velocity is 0 at that point. Initial velocity is 0. And let's calculate the velocity at the ground, right, when it reaches the ground. So initially it is 0 velocity. Height is mg times r. And that should be the same at the bottom point also. At the bottom, there is a lot of velocity, so that's what we are interested in. But the potential energy at the bottom of the surface is 0. Okay. Is that clear? Is that readable? I'm trying to compress everything in a small area of the board. Okay. Tell me if you cannot read it, I can go to the next board if you want. You'll have to tell me only, otherwise I'll keep.
Until yeah, we are okay. We can say.
Yeah. And this should be
Yep,
familiar.
we're good.
You're okay, good, thank you. Mass cancels out, v you can solve for, so velocity is equal to 2 times g times some special height, which is radius r. It's 2 times g times r, right? Something very familiar. So you drop something from a certain height. In this case, I called it the radius r. In uniform gravity, the velocity at the bottom is 2 times g times r. And usually you say this conservation of energy can directly give you that, but I started with the force equation and it led to that almost immediately. And that's your, any question or comments on that? Okay.
Okay.
Okay, if that is clear, so now let's upgrade ourselves to slightly more complicated than this, but not very complicated. So how much time do I have? 9:48. This is supposed to be 1 hour and 15 minute class, right? So I can have 20 more minutes or so, right? I'll finish this and then stop. Okay. Same example, but now it's not uniform gravity. So this is Newton's gravity now. And that's due to a planet. And we know that the gravitational field or the force is equal to, so let's say this is force F is equal to capital G, the universal constant, times the mass of the planet. Now we are talking about a spherical planet. The mass m of the object that is falling divided by how far you are from the center of the planet, that's radius square. And there is a unit vector which is radially outward. Am I missing something? Or maybe I should ask, what am I missing in there?
Wouldn't there be a sign for direction of the force?
Very good. Gravitational force is attractive. I said that is radially outward, so this is negative.
Yeah.
Good. Very good. Okay. Let's say that's our planet, right? That's our, let's say the radius of the planet is r, right? And what else should I say? And let us say, like, I choose my z-axis to be in this direction, right? So that's my z direction. Okay, so, and I'm going to, in general, think of a meteor, like meteorite. When it enters the planet, it usually doesn't enter radially inward. That's very uncommon. It will take a, it will go around in a trajectory. But let's say that for some reason it comes from very far away and there is an object that falls radially inward. The advantage then is that we don't have to worry about the angles. So it's much simpler. Okay. So an object starts from r equal to infinity if you want. So, or let's say this is radial, right? R, right? So radially outward. So it starts from r equal to infinity, and it starts from rest from there, and then it falls down, and we want to reach here. Okay. So what's the equation for that? Mass times acceleration again is equal to the only force that is acting on that, and that's g m over r square times r hat. Since it is radially falling down, everything is happening along the radial line. I don't have to, I don't need the vector. Instead, I can directly say it is m times dv by dt is equal to v now is dr by dt. Like the radius, how fast is the radius changing? And that's equal to minus g m over r square. That's my equation for this problem now, where gravity is not uniform. Again, I can cancel out this m, right? But as we learned there, it is nice to keep the m because then we can identify the kinetic energy. But anywhere gravity comes in, m cancels out. Hello?
Well, I think Dr. Sajist.
Yeah, I think I got disconnected, but I think
yeah.
I'm here, I guess.
Yeah, you're there now.
Yeah.
Huh.
You
I
got
feel like
What
my
happened? I'm back now.
it is gone. I feel like my one is gone.
okay. How much did you miss?
Okay, I think after the gravity is not uniform.
Yeah, so did you get this equation when I was writing this?
For this equation, when this is the equation when the gravity is not uniform, yeah.
Correct. And then I was saying that velocity is dr by dt. And what else did I say? And yeah, what I was trying to tell is that this mass cancels out here, right? And that happens only in gravity. And we always say that when you drop a feather and a bowling ball, like think of a metallic ball and a feather, if I were to drop it, which one reaches the ground first? Let's imagine no friction, no air.
They both fall. They both hit the ground.
Like both hit the ground simultaneously.
Yeah.
And in fact, we say this to, when we are teaching this, we say, oh, that's intuition, that's our equations, but it should be counterintuitive, because we also tell that Newton tells us that mass resists motion. So the more massive object should actually fall at a different rate,
faster.
right? And it's only in gravity, only when the gravity comes in, the mass comes in both sides, so it cancels out. So it's only the gravity, for example, proton or an electron in an electric field. Like which one falls earlier? if you have an electric field, now we're talking about electric force. Proton is heavier than electron. You drop it in an electric field, which one reaches the plate first?
Both would hit it because there's still the electric force still has that Q, same Q. Q's would cancel, just like with gravity.
Did attract and
Is the question clear what I'm saying? So I'm saying there is electric field, let's say pointing down, and I drop a proton, right, which is 2000 times heavier than an electron, right? Proton, electron, right? And I say there is a marker here, some reference line. It's the same height. Which one reaches the line first if there is a race?
Sure, how to help you with that?
should be proton, right?
The proton will reach
Because it's attract to the negative side, which is the electric field pointed at.
Okay. Anyone else wants to make an attempt?
But then they both have the same charges.
Both have the same charges,
So
yes.
as long as if they have different charges, then that will depend on how fast they will travel to the plate, how much of the attractive force would increase if if the proton has more of a positive charge than the electron.
So you're saying it will be the same time, both will reach at the same time, yes.
I was thinking different times. No.
So in an electric field,
That'd be six.
for a different charges, there will be a
Never
force
mind.
acting on it, right?
You're saying constant electric field.
Yeah, there can be forces acting on the charges, right? In electric field.
Yes, of course. That's what is causing it to move.
Yeah.
No gravity. Like this is just like gravitational force on proton and electron is really negligible compared to the electric forces. That's 10 raised to 30 times smaller. So we're just saying in vacuum there is an electric field, proton and an electron is,
I think it's
I shouldn't say drop, it's left alone. Proton will get attracted. Actually, electron will go in the opposite direction, right?
Yeah.
So maybe that's the confusion. So maybe let's say I draw equal distances on both sides. Will this reach first or electron will reach there first? Like there's the same distance.
And they'll reach there at the same time.
They reach at the same time.
Yeah, they reach at the same time.
They'll still have the same amount of force. Equal force will still supply the equal amount of velocity to both particles.
I say that's wrong. Suppose I say that's wrong. Would you like to rethink?
Is it the electron reach the top plate first?
Electron, yeah, and why is that? Give me a reason.
Since the mass is less.
Very good, right? So mass times acceleration is equal to Q times the electric field, right? That's what you would write. Right? Force, acceleration. Acceleration is Q times E is equal to over mass. charge is the same for both, E times E. The numerator is same for both electron and proton. It's the mass that decides. Right? If the mass is smaller, denominator is smaller, acceleration is bigger. So electron moves or accelerates faster, so it will reach first. Good, very good,
Mhm.
right? So what I was telling you, that is more natural, that is more intuitive. Mass resists
Mhm.
motion. If you're heavier, it is hard to move. Right? If you have a truck, it is very hard to move.
Very hard to move it.
Right?
Yeah.
Versus a small thing. But then we get confused because we see this feather and bowling ball falling at the same rate. We think that, oh, it doesn't depend on the mass, but that's very special. It happens only for gravity. Only for gravity does this mass cancel out. That's an exception. In general, mass resists motion. Heavier you are, lesser is the acceleration because it goes in the denominator. Right? So that's the general thing. But anyway, so that's not what we were discussing. That was a digression. So we are talking about something that is dropped, and now at 15 minutes, I drop it. That's my force. Do the same idea as there. Multiply by velocity on both sides, right? dv by dt. And what? Can I do that here? So let's see. So this is minus v, so g m over r square times dr by dt. Correct? I multiply by velocity on left, on the right too. And as we did before, the left hand side is nothing but time derivative of half mv squared, that's kinetic energy. And on the right hand side, there is a 1 over r square times dr by dt. If you notice, if I have d by dt of 1 over r, where r is a function of time, remember, right? It's implicitly dependent on r. That will be the same as minus 1 over r square. Like first take the derivative of r, but then since it is implicitly dependent on time, that's dr by dt. Correct? Which means that I can write this down here as d by dt of g m over r. Take it to the left hand side, and I learn that time derivative of kinetic energy of mv square. And when I put the expression on the right on the left,
Minus
learn that that's nothing but the gravitational potential energy, right? So that's g m over r. That's equal to 0, right? So if something is equal to 0, that must be constant. So you say that, oh, kinetic energy plus this time the potential energy due to gravity is equal to the total energy, right? So let me write that here. Try to use the space. So we learn that half mv square minus g m over r, that's a potential energy due to gravity. Kinetic energy, that's equal to the total energy of the system, right? Very same expression, except that this time instead of mg times the height, we have the gravitational potential energy due to the planet, right? This implies that, so I went up there. Now let's go to the specific problem. We are saying that we drop an object from very far away, from r equal to infinity, with 0 speed. Like I could have thrown, like I sit at the edge of the universe, and I could have thrown an object with some velocity, but I just drop it from there. And we would like to know what is the velocity what will be the velocity right when it hits the surface of Earth. So initially, initially it's at infinity. I start from 0 velocity, so that's 0, right? Kinetic energy is 0 at r equal to infinity. At r equal to infinity, this is also 0, right? Because it's 1 over infinity, so potential energy is also 0. So the total energy is 0 where for the problem we are talking about. But as it goes down, kinetic energy increases, potential energy has to be negative if it has to maintain that 0. So somewhere at the bottom, so we are talking about right at the surface of the Earth, I again have some velocity. That's what I'm interested in. I'm interested in calculating how fast is it moving when it reaches the surface of Earth. And this is G M M over, this time it's a radius of Earth, so that's R. Calculate
Could you
the,
please explain this one again?
is this clear?
Yeah, second, yeah.
Yeah,
I'm
so
asking
now
for this last stage.
So now I am asking a specific question that initial point. So initial point is r equal to infinity, and the initial velocity is equal to 0. So when the object is very far away, so that's this point here, very far away, it is infinity, of very far away, and the velocity is 0. So left hand side
Zero.
is my initial, and the right hand side is going to be my final point, right? So I can say initial is equal to final, correct? That's how you do the energy calculation. At each point, the energy has to be the same. Is that clear? Maybe I should write that down. That will help. So, okay, let me.
I think it's okay.
Yeah, so this will be equal to half mv initial square minus g m over r initial. That's equal to half mv final square minus g m over r final, right? I have to pick 2 points, initial and final. Initial point I chose to be at infinity, and the final point I choose to be at the surface of Earth. Is that clear?
Yeah, thank you.
So then initial point, I said it starts from rest, so that's 0. It's at very far away, 1 over infinity, that's 0. That's equal to half mv final square. And the final point is on the surface of Earth, so it is g m over radius r, right? So, and I'm interested in calculating the velocity. V mass again cancels out. We have just kept it so that we understand that. So put it on the left hand side. V final is equal to 2 times g m over r and square root, right? This has a special name for it, whatever is there on the right hand side. Anyone can recognize that? Very good. That's the escape velocity. Very good. Very good. Right? In the escape velocity problem, we reverse the question. We say that you throw the ball from here. How much should be the velocity of the ball or the spaceship so that it escapes the gravitational field of Earth? That means it has to go all the way to infinity. But let's try to, so that's good, very good. So that's the escape velocity. But now let me manipulate this a little. What's the gravitational field on the surface of Earth in terms of the radius and the mass? Anyone? G is nothing but G times capital M over R square.
Over R.
R square, actually, right? Because it's an
Yeah.
acceleration.
Yeah,
So,
because
right, so it's R square. And if you
it's an
calculate
acceleration.
the mass of Earth is 6 into 10 raised to 24. Radius is 6.4 into 10 raised to 6 meters. And if you put that number in, this comes out to be exactly 9 to 2 digits. It's 9.8 meters per second square. So if you were to write that in that form. So that's r squared and r, right? Just write it in that form. So that's 2 times g times r, which is, if you remember the earlier problem we were doing in uniform motion, right? We got pretty much the same expression, but there are 2 different configurations, remember. In uniform motion, we said Earth is flat, and we dropped the mass from a height r. So the velocity that the mass gains in a height r, where r did not mean anything there, it was just a height. But if you think of it as the radius of the Earth, in this case, that's not the case because it was flat. It turns out to be the same if you were to drop it from infinity, and in non-uniform gravity of a planet's surface, that's sort of a comparison you can have. That's just a coincidence, nothing deeper than that as far as I know. Right. So that's an exercise where you see position dependent forces. In your homework, you will see drag, which is a velocity dependent force. And we will also try to do that. Maybe, I'm not sure whether I'll do that or not. Most of you have seen drag forces. Yeah, here is a quiz, the 4th or 5th question in the quiz. I don't know, I lost count for the quiz. If you do not have drag, that means I am throwing a ball in vacuum. I throw a ball up. How much time does it take to come back in my hand? Calculate and tell me. So I throw a ball with a velocity v up in the air. Tell me how much time it takes to come back in my hand.
And this is in vacuum.
This is in vacuum, no drag at this point.
Two times gt. Oh,
But t is not known, right? I'm asking you for the time.
v over 2g.
V over 2g. Isn't it V over g?
To come back to the hand, to go.
Oh, yeah, come back to the hand. Correct. Good, very good. So V over 2g. Yes, very good. Thank you. Yeah, correct. Is that all? So first question, the quiz is, first calculate the time it takes. If you throw a ball with a velocity v, how much time does it take to come back in my hand? Okay.
It's a 1 time g and then second.
So again, phrase the problem better, because this is going to be more than a quiz, maybe. Okay. So let's say I have a ground, right? Here, drag is 0, right? No drag. No drag. Right. So we are in vacuum. I throw a ball up with velocity v. Okay. It goes up and then comes back, right? And it comes back to the same point. Tell me what is the time it takes to go up and come down. Okay, that should be something straightforward. Kinematic equations, solve for it. I think, how will I do it? So I have to reach the top, right? So V final minus V initial is equal to G times T, right? Right, V final, and it's minus GT, I guess, right? V final is 0, so V initial is equal to G times T. This is the time it takes to reach the top, but it's the same time it is
We
going to take.
missed the right side. We
Huh?
didn't see the right side.
Oh, you cannot read the right side. Thank you. I had to move the boat. Thank you very much. Okay, very good. Okay. So that's a kinematic equation. Final velocity minus initial velocity is acceleration times time. Acceleration is downward. And if I say this is the time it takes to go up, right? Reach the top, initial velocity, final velocity is 0 on top, plus G times T up. So time it takes for the upward travel is V initial over G, right? But then Dilakshi told me that, oh, you have to come down also. So of course I have to add that also, but when there is no drag, it's a symmetric problem. The time it takes to go up is exactly the same time it takes to come down. So the total time it takes is 2 times V initial over G. So it's 2 times, right? Dilakshi, am I right?
Yeah, it should be 2 VOG.
Yeah, I made a mistake. It's
Okay,
divided by 2.
Yeah, I also accepted it. So yeah, good. Thank you. Yeah, good. But at least you realize that you were doing it in your head. So good, right? So that should be clear. So that's the first part. Okay. Now here's a new question. So now switch on the drag. So there is drag now. Okay. Now when you're going up, there is a drag going down. When it is coming down, the drag is up. So the motion is again going to look like this. But now the question is, what is my new time? Okay. And let's say it is the same initial velocity, right? Let's keep the V the same. And you want to have some drag coefficient, all that, put in the thing. Take this question and upgrade this to more than a quiz. If you do this, this is a bonus homework, let's say. You can replace, so there is no deadline for this. Submit it within, let's say, before midterm 1, reasonable. And if you don't submit it, nothing wrong. You don't miss anything. But if you can do it and you get it correct, you can replace it with your lowest homework. How about that? Is that reasonable? Okay. You don't have to do it at all. Don't attempt it. But I think it's kind of interesting. It's not very straightforward. Okay.
It's
But at the
pretty
same
much
time-
doing the same thing, just with air resistance,
Yes.
with drag.
Remember your terminal velocity equation? You probably
Yeah.
teach this in your lab course. Do you do any experiment on lab terminal velocity? No.
No,
Okay, so look up terminal velocity and
but I have worked with terminal velocity before.
good. And let's keep it simple. Let's say it is linear. Usually when you're jumping in air, it is V square because it is not very viscous. Usually in a viscous material, it is linear, otherwise it is quadratic. Keep it simple. In your homework, you work with quadratic drag. Let's say, keep it to be linear and get me the time. Okay. You can use any resource you want, perfectly fine. Just get me the time. Is that question clear? That's it. And I should stop. 10:18, 3 minutes extra. Not bad. Okay.
That's our bonus.
What's that? 3 minutes bonus? Is that right?
Yeah.
Okay. Thank you. So see you guys next in the classroom in 410. Hopefully we don't have to do this too often. This makeup. So this is an exceptional scenario. So
Okay, I have
So,
something to know. Yeah, all the homeworks problem are coming through the Goldstein, or that one is just for the different?
no, it's not going to be from Goldstein.
Okay.
Yeah. They're motivated from various textbooks, and then I rewrite them in my own words.
Okay, it's a combination of the different books.
Yes. And if it is exactly from a book, then I write it down. Yeah, some things you should be familiar with. If you go to the web page, there is I can share the, can I take a few more minutes?
Okay.
yeah,
Oh, I know it's late, but I think maybe I can share the screen. Let me see. Can you all see my screen?
Yeah.
Okay. So let's see. So this is a course web page. You should be able to reach here.
Mhm.
First of all, I noticed that most of these textbooks are available in archive.org. Like if you click on this, even though I don't specify this, if you click on it, it directly takes you to the textbook.
Okay.
So you can download them. So at least you have online versions of it. And archive, I presume, is a legal place. Most of this textbook, I think, are so old that they make it available. I don't know that, but at least they are available there. And archive is a decent place. So I think I can give a link for that. Hopefully, I'm not violating any copyright. Issues. But these are all old textbooks, so I hope it's all fine. Okay, that's one information. Syllabus, of course. Notice lecture recordings were done for this course 3 times in the past. I will add a link for this semester also here. So you can see my mouse, right? Right. So
Yeah.
each of this is a playlist. You can see lectures from the past. Sometimes they are useful. I don't know how useful they are, but it's available for you guys. This one you notice informal notes. I haven't done this in the past, but this is all the questions I have collected. So I'm going to click on that. So let's see. This is all the questions I have collected for this course in the last few semesters. Okay. So if you look at this, this is, for example, position dependent forces, right? So whatever we are doing here now, whatever questions I have collected in the past is there here. So for example, that's one, like radial free fall of meteorite. That's what we did today. I have not typed them, but if you go to the lecture of 221 spring, dated 21, you can see that I discussed this there also. So, but I never typed it down. So similarly, you can talk about a pendulum. This is something I've done in the past. This is about how much time does it take for a ball to go through a tunnel in Earth. So various problems I have collected here. You should be able to go through it and see it. Almost everything I have ever typed is available here.
Okay.
So that should be a good resource for you guys. Okay.
Okay.
Is that clear? And then I have old exams. So all the web pages for the past classical mechanics courses is here. So I have taught this about 6 times before. This is the 7th time I'm teaching it. So these are the web pages for all the past courses. For example, 2022 spring. It takes time, I guess. Come on, go. And that's your 2022 spring, and all the homeworks are available. I sometimes change the homework. Sometimes I keep the homework the same, and that's useful. Sometimes it's not. And if you go further into the past, there are also typed notes, handwritten notes available. In the very first times I taught, it was only handwritten notes. So these are all resources. Sometimes it's useful. I know often students like to have these kind of questions, so it's useful, but it's not necessary that you need to use it. Technically speaking, lecture notes and the textbooks should be, or reference books should be sufficient. Okay. And here, unlike last semesters, I'll start collecting what are the topics I'm discussing. That should be useful. You should be able to use those keywords and find things around. Okay.
Okay.
So that's something slightly different from earlier semesters. Okay. Any comments or questions you have?
Okay, this much is good. Thank you.
And I cannot stop this now. Come on.
You can cut that one, I guess.
I cannot stop sharing.
If you move your cursor to the top, it will come down, I think.
No, I can see the stop share as a red button, but I'm clicking on it. Nothing happens. Okay, it doesn't matter.
Maybe it's slow or something. I don't know.
I don't know. Come on. Can I annotate? Yeah, I can annotate, but I cannot. Now it stopped.
Oh, yeah.
So it waited for me to annotate it. Okay, doesn't matter. Okay. Oh, I should change the camera. Now you cannot see me, so yeah. Okay, that's it. So good. Thank you for listening to me at this late night. Probably some of you guys sleep early, but thank you. So at least we started the course. Otherwise, it
Yeah.
would have been too late.
I have a class. I have a lab tomorrow morning.
Okay.
Early.
Okay, at least
Yeah.
some little bit of sleep.
Yeah, I have to prepare.
Oh, wow. Okay, sorry
Because
about
it's
that.
my first class. It's okay.
Okay, sorry. Okay, thanks.
That's why I'm just starting the preparation. I have to little be prepared, and
Okay.
then tomorrow.
Blame it on me if it doesn't go well. Yeah.
I hope that will I will make it good.
Good. Okay.
Yeah.
Okay.
Mhm.
Okay, thank you. Good night.
Okay,
Enjoy.
Yeah.
thank you.
Yes.
Good
Good
night.
night.
Thank
See
you.
ya.
Mhm. Bye.
See ya Thursday in class.
Yes. Thank you. Yes. Thursday in class 9:35 a.m.
Okay, not a PM.
Okay.
Yes.
Yeah. All right.
Okay. I'll
Alright.
let you guys go leave. I'm the host, so I should leave last, I guess. Yeah. User?
Yes.
Okay. You will be leaving, correct? Yeah.
Yeah.
I'll let you leave first and then I'll. Okay.
Bye. Good night.
Yeah. Bye-bye. Good night. Thanks.